What we're going to do now is we're going to take a look at another driver program that uses the concurrent map collector. But if all goes according to plan, it'll give us different results than the version that we did before. And I want to talk about why it gets different results, because it's important to understand the trade-offs between the types and the overheads we're about to talk about. So this uses concurrent map collector just like we did before. But this time, the test program itself is going to compute the greatest common divisor for various sized lists of randomly generated integers. And because of the fact we're using greatest common divisors and integers as the keys for our map, the merging costs are going to be different than they were for the previous example where we used strings. So it turns out that doing merging of tree maps in particular with strings is more expensive than doing merging of tree maps with integers. And therefore, we're likely to see different results than what we had before. So let's first go ahead and run the program, and we'll see what the results are. And as you'll see here, when it runs, it's going to once again generate different sizes of random parameters to check whether their greatest common divisors are. And it's going to have them for 1,000, 10,000, 100,000, and 500,000. And I'll show you how that all works, but I want to show you the results first. We'll see if the results are a little different from what we had seen before when we ran the previous example, which was looking at the words in the complete works of Shakespeare. So let's go ahead and take a look. This thing is obviously taking a little bit longer to run than before, but it worked. So the first thing to notice here is that for the HashMap version of this, again, when we had 500,000 of them, the parallel concurrent version is a win, and not just a win, but a big win. So you can see that when you have data structures like a hash map that don't have high merging costs associated with them, then the concurrent hash map is just a win again for the same reasons it had in the previous program. And the parallel version was fast, but not as fast. So you can see that the concurrent hash map version for parallel streams is the winner. But when we come down here and we take a look at TreeMap, then all of a sudden we get some very different results. And this seems sort of troubling at some level, because now we're seeing that the parallel non-concurrent version is winning. So all of a sudden using the concurrent hash map really isn't really a win. And in fact, this is probably a quirk because of the fact that I'm running Zoom. And so at least one of my cores is off keeping track of Zoom and videos and stuff like that. So I don't have all my cores at my disposal like I did when I ran this thing without Zoom on. But notice that the parallel concurrent tree map is actually a little slower than the sequential non-concurrent tree map. And that indicates that the time for doing the merging at the final stage is high, because what we're doing there is we're taking 500,000 elements and converting them into a tree map, which is taking some time. So the point is that you don't always get the same results, even when sometimes you get a win, and it really depends on the data types that you're using. So let's take a quick look at the program itself, just so you can see what it's doing and how it compares and contrasts with the one we looked at before that had the complete works of Shakespeare. So in this particular case, what we're going to do is we're going to generate 1 million numbers, and these numbers are going to be 1 million random numbers. And we're going to take those 1 million numbers and we're going to go ahead and create a stream of GCD param objects with 2 random numbers here. First is the first number we're going to use to compute GCD, and the second is the second one. And let's take a quick look at GCD param. GCD param is a record, and a record is a special kind of type constructor in modern Java, as of Java 14, that doesn't have the overheads that a normal class does. And in particular, if you think about what a normal class has in Java, if you use a class as a data container, it contains some other fields in it. It contains a v pointer, for example, virtual pointer that points to the virtual table. It also contains an intrinsic lock, basically a mutex. It contains an intrinsic condition, basically a condition object. So every instance of an object of a class in Java will have some extra state. And if all we're trying to do is just store 2 values, first and second, to compute GCDs, we're basically doubling or more the size of each of the objects. So by using a record, we don't pay that overhead. So we just have the contents first and second, and that's it. Now, this particular record is also going to implement the comparable interface. So we're probably going to have a V pointer as well, but we won't have all the other fields that would be part of a normal Java object. And this is just demonstrating that a Java record can implement interfaces. And in this case, we use this interface to define a compare to method that will allow this particular type to be used in a tree map that expects to be able to order the contents of the map. And we just basically do this by subtracting the first elements from this object and the right-hand object if you're comparing two elements. And if they're not equal to zero, we return that element because we already know the relationship. If they were equal to zero, when you subtract one from the other, then we go ahead and subtract the second field from each of the elements to see whether they're ordered or how they're ordered. So that's just using that clever technique that gets used a lot in C programs to do comparisons. So we have ourselves basically a list of 1 million GCD parameters. And then we go into our main program, and it's organized very much like we had before. In fact, the main difference is just what the time stream collect method does. And you'll also notice that the key mapper and the value mapper are slightly different. And we'll talk about that in a second as well. So here's time stream collect. You can see what we do here is we take the test type, a Boolean to indicate whether they're parallel or not, a list of GCD params of various sizes, and then a collector that collects GCD results into a map of GCD params and integers. A GCD result is simply going to be the GCD param integers, like two values we want to use to compute the GCD, and the result of that computation. So that's what GCD result is. So we take a GCD result, and we end up with this map as the result. So all this test does is it runs for a number of iterations and calls this helper method and times it. And the helper method takes the random numbers that are passed in, which again will be of different sizes, like 1,000, 10,000, 100,000, 500,000, converts them into a sequential stream. And so we first convert into a sequential stream. And then we can conditionally convert into a parallel stream. And then we go ahead and we call the compute GCD method, passing in the GCD parameters. And you can see that this just creates a GCD result, passing in the GCD parameters after calling the GCD method on the integers. And this is just a non-recursive Euclidean algorithm implementation of the greatest common divisor method or algorithm. And so that gets us back a GCD result, which is also a record. And so you can see we're using records everywhere, as you should in modern Java. And then we collect that into the right collector. And that's what the driver program does. And all we do up here is pass in the key mapper and the value mapper, which just are the GCD parameters and the result. So that's how that works. And then run collector tests works pretty much identically to what we did before. We get different tests for different sizes of input, and we go ahead and get that many number of random objects. And then we go ahead and call these methods to do the work with the different variations of parallel streams, sequential streams, concurrent collectors, and non-concurrent collectors. And again, as you saw in the results are slightly different this time because of the differences in the data types, where the merging costs are going to be lower in general for this test. And therefore, we're not going to pay as much of a penalty for merging as we had with the earlier example where we use strings, which have a higher penalty for merging for things like sorted tree maps.